This suggests that now some poor schmuck could have created an entire table of these things. And here's our table. So these are the ones we'll use a lot. The transform of an impulse is 1. The transform of a step is this thing. Transform of a exponential is this. Of course, you could handle a to the negative n too. It's just 1 over a here, so this would be 1 over a. I've got a few other ones that you can take the transform of. And soon we'll be talking about these properties too. And it's the same one you've seen before for linear time: linearity, time shifting, differentiation. If you'll remember vaguely, differentiation in the continuous time was like multiplying by s, and this is going to be like multiplying by z, negative z, but still multiplying by z. And convolution in the time domain is like multiplication in the frequency domain, which is the big useful part of this. Take a look at this thing. This impulse transforms to a 1. And down here, this time shift, a time shift of -3 is like taking the z transform of your original untime shifted thing and multiplying it by z to the -3. Maybe now it's clearer to you why we use for a delay element in our block diagrams z to the -1. If you delay your sequence in time by 1, it's like multiplying it by a z to the -1 in the frequency domain. Let me give one quick example of how to use this. Let's find the z transform of a finite length sequence. So far we took the z transform of an infinite length sequence. Let's take it to this finite length sequence. Kevin, what's its length? What's the capital N of this sequence?
3.
Right, even though it goes up to 2. And Eric, how would you write this as a sum of impulses, of delayed and shifted impulses?
It would
I'll write
be
the
impulse of n minus impulse of n minus 1 plus impulse of n minus 2.
Yeah, no problem. All right. So Jeremiah, if you remember our previous slide, this is going to be a test of your recall. What is the z-trans? We can use linearity to say the z-transform of this whole thing is equal to the z-transform of the first part minus the z-transform of this part plus the z-transform of this part. So can you start us off with what the z-transform is, x of z, of just this first part?
It's 1.
It's just 1. All right. Well, that was so easy for you. I'll give you the next one too.
And then z to the -1 times 1.
That's it. So it's 1 times z to the -1, and just finish up for me.
Same thing, but z -2.
Yeah, that's it. So this is another great power utility of the z transform. That sure you can figure out infinite length z transforms, but you can just read out that transform for a finite length sequence right away. And then I don't think anyone remembered this, but this is if you need to find its region of convergence, it would be for almost all z. Finite length sequences always converge over the entire z-plane with one exception, and that is 0. If you plug in 0 into this guy here, you get 1 over 0 and it blows up.